It's recording. So hello everybody, and so we're gonna continue with the molecular orbital theory. So last time we were talking about the theory, basically how to interpret that and how to draw the different energy diagrams for different molecular orbitals. So you know the basic rules that n number of atomic orbitals will form the n number of molecular orbitals. So for example, if you have two s orbitals, atomic orbitals, when they will form a sigma bond, they will form a sigma bond and sigma anti-bonding orbital. And of course, the bonding orbitals are lower in energy than the initial atomic orbitals, and the anti-bonding orbitals are higher in energy. We also know that each and every orbital can carry maximum of 2 electrons, and we also know that if there are more than one molecular orbitals of the same energy, the electrons will fill up 1 electron per orbital first, and then once they fill up all the orbitals with the same energy, they will start filling up the orbitals with the second electrons. And we talk about different aspects of it, and so in general, we are interested in two different types of bonding: a sigma bonding and the pi bonding. And you know, throughout examples, we move into this acetylene example, which is an example of the molecule with the triple bond here. The triple bond means there is one sigma bond, and there are 2 pi bonds. So if you look at the diagram here, the sigma bond is formed by the interactions, in this case, on the sp orbitals along the x-axis here. So this is the one in yellow, and the bond formation is in the middle here. This is the carbon-carbon sigma bond. Also, there is a sigma bond between carbon and hydrogen. This is another yellow part here. Okay, and then you have these 2 p orbitals. So the one that goes around x-axis and z-axis, and they can also interact, but not head-to-head, but sideways now, because of the orientation in space. And the sideways interactions allow you to form the pi bond. So you have 2 p orbitals, therefore there are 2 pi bonds possible to form. And of course, the orientation of those orbitals has to be the same in order for them to have a constructive interaction, which is the pi bond formation. Okay, so in our case, we have 2 pi bonds here, and what will be the molecular diagram for this particular molecule? Well, there we go. If you look here, you can see the molecular diagram for the triple bond here, not the sigma bonds that are on the sides, but just the triple bond in the middle. So how do you know if this is the triple bond? Well, what do you think? How can you check if you have a double or triple bond, you know, without seeing actual structure? So if you look at the molecular the energy diagram here, so the energy goes that way. How can you figure out if you form a single, double, triple bond? What do you need to calculate? Yes, Deborah?
You use the formula where you subtract the anti-bonding from the bonding orbitals, and then you divide it by 2, and you see how many bonds you have.
Yeah, so what is it called? It's called a bond order, correct. So you first have to calculate the bond order. In our case, if you look at the molecular orbitals, we have a sigma orbital here and p orbitals here. And the sigma and pi orbitals, they carry 6 electrons. How many anti-bonding electrons are here? You look up here and you see 0. Yeah. So 0 divided by 2, that's 6 over 2, which is 3. Yes, Chantel?
Wait, where do you get the 6 and what does it 6 mean? 6 electrons?
6 electrons, 2, 2, and 2. You look at the molecular orbitals, not on the ones on the sides, the ones in the middle here.
They just
Yes,
look
Guna?
like arrows to me. I don't.
Yeah, these are electrons. So electrons are represented by arrows, half arrows in this case, actually.
Professor, I have a question. Can we see the example where we have some electrons in the anti-bonding orbitals?
Yes, we will have them. Yeah, so just give it a moment, okay? So the first thing you do here, so there are no electrons here, here, and here. These are the pi antibonding and sigma antibonding orbitals. So therefore, the second value is 0 here. Okay. So once you calculate the bond order, you know that this is a triple bond. Okay. And then you see that you have a sigma bond that is lower in energy, and then you have a pi. Sigma. I'm sorry, not sigma. The sp hybridized atomic orbital that is lower in energy. Then you have the p orbitals from these are all from carbon. Okay. And of course, on the other side, there is the same scenario because this is the carbon-carbon triple bond. Okay, so therefore the energies of those orbitals, the sp and p orbitals, will be the same. And we know that sp and pz and py here, they all carry one electron only. So we are not looking at this side of the molecule. So this extra one electron that is involved in the formation of a CH bond is not involved in this diagram. It's only triple bond from carbon-carbon bond. Okay, and we know that one electron from the sp orbital will interact with another one electron from the second sp orbital, and this is actually sp orbital, yes, to form a sigma bond. And you see the cartoon representation of the orbital. You have this larger part and the smaller part of like an 8. Okay, so now that has a different proportion. And the bonding interaction here is shown as this a new structure here that has this elongated larger portion in the middle and then two smaller parts on the sides. So this is how you represent the sigma bond. And it's a bonding scenario, okay? Yes, Chantel?
So back to the bonding order formula. So does the order of like what the numbers of the electrons matter? Like, how do you know that 6 would go first compared to 0? Like,
well, so these are 6 are bonding orbitals. So electrons on the bonding orbitals, and the 0 in here are electrons on anti-bonding orbitals. So the bonding is just sigma and pi. Anti-bonding, they have this asterisk here. You see?
Mm-hmm.
So asterisk means that these are anti-bonding orbitals. So basically, the sum of those without asterisks minus the sum of those with asterisks, electrons, of course, yeah? That will be your bonding order, okay? And, like you can also review the previous class. I think we did that, quite well over there, yeah? Yes, Gunnar?
Yeah, Professor, so the diagram at the bottom, does that represent the triple bond or does that also represent the triple bond and the single bonds too?
Well,
the
electrons at the bottom or the red line?
No, the diagram is the one above the electrons.
Yes, so these two diagrams. This is the diagram.
The diagram, like
this one,
the bottom one. I think you said it represents the triple bond.
Yes, so this is molecular diagram for the triple bond. The whole thing. The whole thing here. All those electrons and all those cartoons that are drawn, they represent the molecular diagram for the triple bond. Okay.
Got it. Are we going to be responsible So, like, are we going to draw this on the test too, or?
Well, I'm thinking about it yet. Okay, so I will let you know definitely before the exam. Okay.
Okay.
So here we have a sigma bond. Okay, so this is, like I said, head-to-head interaction along the x-axis here of two sp orbitals. Okay, and then you have a pi bonds. Okay, so the pi bonds are higher in energy. You can see that on the MO diagram because they are basically higher, so they are above the sigma, yeah, bond, but they are also lower in energy than the separate p orbitals. And you see we have two p orbitals, pz and py, and of course on the other side pz and py. So py will from the right side will interact with the py from the left side, and pz for one side will interact with the pz on the other side. It's not pz with py. It's always the same orientation, unless if you have a different orientation, there will be no bond. Also, as you can see here, the in all of those examples, the one part of the cartoon is darker. So the darker part means this is the sign of your wave function. So to have a constructive interactions, the sign have to be the same. That's why it's darker in the middle here, because the darker part interacts with the darker part. Okay, if you compare the sigma bonding interactions versus sigma anti-bonding interactions, which is all the way on the top here, you see now that the wave function is different between two sp orbitals. So you have a dark part versus the white part here, or lighter part. Okay. So that means that those wave functions have a different sign, and therefore there is destructive interactions, not constructive interactions, and there will be a node form in the middle here. That's why it's called anti-bonding orbital. And then if you look at the p orbitals, well, you have, first of all, you have a pi bond formations, and these are represented by these two structures here. And you see the cartoon shows it sort of like in the 3 dimensions. So the one on the left side is the pi z. So z means that it goes along the z-axis. And you have on top of that, you have the higher, you have the wave function with the now of the molecular orbital with the same sign, and then at the bottom you have the one on the different side. And basically the same thing happens on the y part, but then you have then these two regions are separated by the y-axis. That's why you don't see it as clearly as on the z part here. And as you see, the p orbitals versus sp orbitals, they differ in shape a little bit. So the p orbitals are more like an 8s, yeah, while the sp orbitals are disturbed 8s, okay, with the larger part on the one side. And then if you think about it, we have 3 electrons here on the sp and p orbitals. Just one second, okay? And so one of these electrons goes to form a sigma bond, and the remaining 2 electrons will interact with another 2 electrons from the another p orbitals to form a pi bond. Yes, Gonit?
So the reason why we chose only 2 orbitals for 2 p orbitals out of the 3, is it because we have 2 pi bonds?
Well, no. If you think about it, okay. So look at the hybridization pattern here. You have an sp hybridized orbital. So there are 3 p orbitals. One is already involved in the formation of the sp hybridization. So therefore, there are only 2 left. Okay. So like if you have a single, if you had just a double bond, okay, then there will be only 1 p orbital, and the orbital at the bottom will be sp2. Does it make sense?
Yeah, it does. So if we had, let's say, if we only had single bonds, then we would have only 1 s and 3 px py pz, right?
No. You will have, if you had only sigma bond, so 4 sigma bonds, then you will have only sp3 hybridized orbital. Atomic orbital, sp3, because all of them are sp3 hybridized in order to form, at least for the carbon, yeah, in order to form only single bonds.
So we would just have one, just two electrons. We would just show two electrons combining, right? We won't need p orbitals for that.
Yes. So in here, what you see here, we have two electrons because, you know, again, if you think about it, okay, we have a carbon, okay. This carbon is connected with two sigma bonds, and so that means that there is one electron here from the carbon. The other one is from hydrogen or from the other substituent, doesn't matter here, okay. And then you have two additional electrons that are on the p orbitals that form the triple bond. Okay, so since this diagram only shows that part of the molecule, that means that you see only sp hybridized orbital and only 3 electrons. So that's why you have only 1, 2, and 3 electrons. 1, 2, and 3 here. The fourth one is not shown here because this diagram doesn't show the CH bond formation. It shows a triple bond formation. Okay. And as you remember from the hybridization, when you start with the 3p orbitals on carbon, you have 2s and 2p orbitals. You have 4 electrons on the carbon, and they will undergo hybridization. And in this is sp hybridization, so that means only one of the p orbitals will be hybridized, and you will form 2 sp orbitals and 2 p orbitals. Each and every one of them will have 1 electron now. Okay, so out of these, so these are the 2 p orbitals, and these are sp orbitals. Okay, so now out of that, we use only 3 electrons to show the triple bond, because you need 3 electrons to show the triple bond because you have 1 sigma bonds and 2 pi bonds, and the remaining electron here will be used to form the CH bond. Okay. Okay, bond order. The first value that you put in the equation is the number of electrons on the bonding orbitals. Bonding. Okay. The second value that you put over there is the number of electrons on anti-bonding orbitals. So if you look at our molecular diagram, we have 2 electrons on the sigma bond, and then 2 electrons on the pi z, and 2 electrons on the pi y. Each and every arrow here represents 1 electron. We have 6 arrows, 6 electrons. Then you look at anti-bonding orbitals that are represented here. So sigma anti-bonding and pi anti-bonding, and there are 0 electrons on each. So that's why the second value is 0. Okay. So going back to the p orbitals. So constructive interactions will show as these two different cartoons, which are basically the same but oriented differently in space. So the first one goes along the z-axis, the other one goes along the the y-axis, and then the non-constructive or destructive interactions, which are the anti-bonding orbitals, will be basically your p orbitals, but drawn one by another with the different wave functions on the opposite. With the different wave function on the same side of the bond. Okay, so you see in here we have a let's say dark area that is next to the lighter area. So that means that these two wave functions have a different values, different signs. So therefore, there will be no constructive interaction here. And the same happened here on the y-axis. Yes, it was wrong because then you will get the negative value, yeah? Chantel. And you cannot have a negative value for the bond. You can have a 0 value, which means no bond, but not the negative value, because what you just, I don't have non-bonding divine space or something, I don't know. Okay, and then I already told you about the sigma bond here. Okay, so again, if we go back to this diagram here, we know that energy increases up. The bond order tells you the number of the bonds that forms between two atoms that are being described in the molecular orbital diagram. So let's say that this is carbon number 1, this is carbon number 2. Okay, in your triple bond, you combine the atomic orbitals of carbon number 1 and carbon number 2 together to form sigma bond and pi bond. Okay, since this is a triple bond, and that means that you have to have at least two p. I mean, you have to have two p orbitals that will interact with each other. Okay, to form the pi bonds. This guy here and this guy here. So the what is the sigma antibonding orbital above the sigma bonding orbital, and the pi's are above too, you know. Oh well, why can't you form the quadruple bond? So think about it this way, okay? In order for you to form the quadruple bond with the s and p orbitals, you would have to have all the p orbitals on the same plane, so they can have the side-to-side interactions between one another. It's impossible geometrically for this particular molecule to form that. If you have a d orbital, there is a possibility for quadruple bonds, but not with the s and p orbitals, unfortunately. Okay, so the only options you have really are sigma bonds, double bonds, or triple bonds, not quadruple bonds. Okay. So as far as Deborah's question here, so the sigma bonding interaction is the strongest interaction, therefore the gain in energy is the highest. Okay, that's why it goes all the way down here, and therefore the anti-bonding interaction has to be even more destructive than its bonding interaction. Therefore, it goes all the way up here. The pi bonds are weaker bonds separately. Okay, so that means that the energy difference between bonding and anti-bonding pi bonds will be smaller, and that's why you know they are in between there. And also the other thing is that this is the theoretical situation. There are situations where the sigma bonds anti-bonding might be lower in energy than any anti-bonding for the pi bonds, but you know, we are not going to deal with those. Okay, so don't worry about that. Yeah, what you want to do here is that you need to understand the fact that in the formation of the triple bond, you need to know from the hybridization that there are two sp orbitals and two p orbitals. One of these sp orbitals is used to form the sigma bond between two carbons, carbon 1 and 2, and two of the electrons from the p orbitals are used to form the pi bonds. So let's call it pi 1 and pi 2, or pi z and pi y. Okay, so this is something that you just have to know. Okay, so if I were to ask you what is the MO diagram for, so this is MO diagram for the triple bond. So what about the MO diagram for the CH bond here now from acetylene? Okay, I'm going to do it in green here. H. Let me try again. CH bond here. Okay, how would you do that? So now Again, it all depends on the question. So I may ask you the question about, okay, why don't you draw me one of the pi bonds from the triple bond? Okay, I can do that. I can also ask you to draw me a sigma bond from the CH bond here, and ask you what would be the diagram for that. And then, well, all you need to do is just start with drawing the direction of how the energy will increase, and then you know that the hydrogen has one s orbital, and the carbon here, because it's with the triple bond here, it has sp orbital that will interact with one another. Okay, so then we have the one s orbital here, and then we have sp orbital over here. So this is our hydrogen, this is our carbon now. And you form only one single bond here. So that means you form only sigma bond here, okay? So the sigma bond will be lower in energy. And of course, if you form a sigma bond, you also have to form a sigma anti-bonding orbital. So now, remember from the previous slide, we have this blue electron that is on the second sp orbital that is not shown in this this energy diagram. So this blue electron now is here. Okay, another blue electron comes from the hydrogen, and as you can imagine, those two electrons will have to be combined together to form this sigma bond. So therefore, they will move down to the sigma bond part of this diagram. And since there's only one electron from each and every element here available for these formations, therefore the anti-bonding orbital will remain empty. So if you think about it, now you have the now you have the full diagram for the CH bond formation in acetylene, okay? And there's only one thing left here, actually two things left here to in order to complete the structure. So the first thing is you can calculate the bond order here. So the bond order will be two electrons from the sigma bond, okay? So 2 minus 0 electrons on anti-bonding divided by 2, so that's 1. So we know that there is a one single bond here formed, and that's true because our green bond is a single bond. And the second part that you will have to do here is that you will have to draw the shapes of the atomic orbitals and the molecular orbitals that will form from the formation of that. So you can start with the atomic orbital of 1s. What is the shape of the 1s orbital? Anybody? It's a sphere, yeah? So all you have to do is just draw the sphere, okay? Then what is the shape of the sp orbital? Well, you don't have to look far, you just look around here and you see that the sp orbital will look like this, basically, yeah? I'm gonna make the darker part now on the, a smaller part, okay? So the constructive interaction here between s and p orbital will be basically something that looks very similar to sp. It's just a little bit larger part of the, the one side that is already larger in the will have to be just slightly larger because it has to accommodate what is it called, the s orbital here. Okay. So just need to remember that this has to be a little larger. Okay, and then how about anti-bonding orbital? Okay, well then if you start with the our sp orbital as a template and s orbital on the other side, what else do you need to change here in order to make this a valid anti-bonding orbital? Yeah, of what now? Which side? The s orbital or the larger part of the p orbital? Yes, the s orbital, because it's already set up for the sp orbital with the darker side on the on the right side. Therefore, you have to change the sign of the s orbital. Gurneet, yes.
Yeah, I just wanted to know, does it matter which side we draw the darker circle on, and which side we have?
No, it doesn't matter as long as you draw them properly. So that means that you keep the same pattern along the whole, along the whole, draw, along the diagram. Okay. So for example, if you, for example, had the two, let's say, sp orbitals interacting with each other, and you want to show the sigma formation, the orbitals that you draw, like in here on the sp orbitals, they have to be oriented properly, and they have to have the right sign facing, the right direction. Let's call it this way, okay? So you cannot draw this, for example. Okay, because that suggests that the interaction between these two orbitals is will be, destructive, really. Yeah. Okay.
Got it. And also a question on the diagram for a sigma star. Why shouldn't the two circles, empty circles, shouldn't they cancel out each other, and we should only have a small shaded part?
Could you repeat, please? What should cancel each other?
So the diagram for hydrogen, we have just a sphere, and then for sp we also have an empty sphere. Why don't they cancel each other out for the? And
no, this is not the the sp is not a sphere. It's a sphere with a little bit, it's like a change, elongated 8 on one side. So it's just a smaller version of it. They don't cancel each other. What happens here is that since this is constructive interaction, so they increase the concentration of the electrons, or the area where the electrons can be found on one side of this wave function. You see? So this s orbital adds additional volume where you can find electrons by forming a sigma bond here. So it's not, it's a mathematical what would you call it, the representation of the electron density around the sigma bond, basically. Yeah.
Yeah. For the anti-bonding diagram on top, shouldn't the circle, shouldn't it get a bit smaller?
Well, it doesn't matter here. Okay. So see, I'm not going to be very picky about, let's say, proportions here, okay? Because I know everybody has a different handwriting, okay? And then the idea is that you show that the s orbital, and then sp orbital in this case, in the right order with the right wave function sign, okay? So basically, in our case, for constructive interactions, you have to have the light part here interacting with the bulky light part, the white part here. Okay. And for the non-constructive interactions, one of the, so in this case, we change the sign of the s function has to have the opposite sign to what it used to be, compared to the part that's supposed to interact with it. So in this case, our sp orbitals remain the same as before. So and you see the change, the shape is slightly different between what I drew here and what I drew here. Is just because my handwriting is not like I cannot just copy and paste it. Let's call it this way. Just by drawing it. Okay, so it's not a big issue if you change the proportions a little bit, as long as they resemble more or less the structure of either sp orbitals or the p orbitals, and the signs of the wave functions are correct.
Okay, so for this part, you only showed them interacting with each other. You didn't show like the result, right? Like for the bottom one, you showed that the circle got bigger, but for the anti-bonding part, you only showed them interacting with each other, like you didn't.
Yes, because this is what happens, okay? So because there is no interactions, the shape of those don't change really that much. Okay, so there is no change in the bonding, kind of like cartoonish version of the bonding. Okay, so I'm pretty sure that there is some sort of change if you look at the actual diagram, and I think we should be able to see it on the next slide. But the idea is that when you draw it, you're not drawing the realistic situation. You're drawing the cartoon of what it more or less looks like. Okay.
Got it.
Okay,
Okay.
let's move on to other bondings here. Okay, so here we have a molecule, and this is the molecule that has the something what is called the CO bond. Okay, so it's either an alcohol or a carbonyl. It all depends, and how do we know if this is a double bond, for example, or a sigma bond, okay, drawn here? Or is it a sigma or pi bond form? Well, you just look at the diagram and see what's drawn underneath here. And we see over here, we can see that it says pi. So that means this is the part of the double bond. That means that the carbon-oxygen bond here is an actually part of the double bond formation. And as you can see here, we have now a p orbital. So this is 2p, let's call it 2pz orbital, from the carbon interacting with 2pz orbital. From the oxygen to form the pi bond. Since each and every one of them carries one electron, they form the pi bond very nicely. Pi anti-bonding part is empty. Okay, and you see on the right side, you see the computer-generated electron densities of the new pi bond. As you can see here, there is a node between the top part and the bottom part, because the two different wave functions, two p orbitals, they interact with one another above and below the sigma bond here. Okay. If you look at the anti-bonding part here, it's basically the same thing as like two empty orbitals. Two like p and z p orbitals, but they just have a different wave function number here. So you see the red part is next to the green, the blue one, instead of just red with red, like it is at the bottom. Yes, Deborah?
Why is this a p orbital as opposed to a sigma orbital?
Because this is the part of the molecular diagram that shows you a pi bond. So it's up to you to choose which one you want to show. Okay, you can show all of them, or you can show just one.
Is there a sigma bond in this molecule, though? There has to be.
Oh, yes, it is. Yes, it is. Yes, it is, but it's not shown here. So there is a sigma bond here. But this diagram shows only a pi bond.
Okay. And there's a double bond between the C and the O?
Yes, that's correct. Because you see, it says pi bond here, so it must be a double bond, yeah? And Daniela, you're welcome. Daniela went on the middle energy. Okay, so here. Okay, so Daniela, in here, in order for this diagram to show the anti-bonding orbital, the wave function sign has to be different than the one that it wants to interact with. So at the bottom, you see you have this bigger kind of empty or white region. Okay, that was made by interaction of this s orbital with this part of the sp orbital. But The anti-bonding interaction is happens when you have an opposite sign of the function. So since we haven't changed the signs on the SP here, it's the same as on the bottom here. That means that you have to change the sign of the 1s. So darker means it's an opposite sign to the wave function that was before. Okay. So this is an example, okay, of the question that you might see actually. Yes? So I may ask you, okay, draw me a sigma bond interaction here or pi bond interaction, okay, and and then or molecular orbital diagram, and you know every time I will ask you about drawing the diagram. This diagram will have to consist of the arrow that shows increasing energy. You will have to show the atomic orbitals, so this guy here and this guy here. And also you have to show both molecular orbitals or more if there is more needed. And and they will have to be properly labeled, so either for sigma bond or pi bond, like it is in this situation. And of course, if you have a sigma bond, then you have a sigma anti-bonding orbital. If you have a pi bond, you have pi anti-bonding orbital. Okay, and you also have to be able to draw the cartoons, so those parts here of the orbitals, or at least recognize them. There is no example where the energy is decreasing. You don't flip the molecular orbital diagrams upside down. Yes.
So so even in this case, we have 1 sigma and 2 pi bonds, right? So can we say that
actually you have 3 sigma and 1 pi bonds, because if you think about the carbon, unless you're talking about the oxygen. So if you're talking about oxygen, you have 1 sigma and 1 pi. But this part shows only the double bond. Okay.
So it only shows one pi bond, right?
1 pi bonds. Yeah, that's correct.
How would we show the other 3 sigma bonds?
Well, you can show them actually together, yeah, on this particular diagram, or you can draw them right next to it. Okay. It's really up to you. I'm going to have some examples for those, on those in a moment. Okay. Okay, so this is another thing. This is a good question, Deborah. Okay, so it turns out that you have a p orbitals. Okay, but those p orbitals, like in this case 2 pz orbitals of the carbons and oxygen, they vary in energy. Okay. So it turns out that the carbon 2 pz orbitals are higher in energy than oxygen. In general, like for most of the molecules that we will draw that are hetero molecules, so like carbon, oxygen, carbon, nitrogen, and carbon, hydrogen, you have to show that there is a difference in energy, and okay, let's see if that will help. That there is a difference in energy. Did it help? Yeah, and normally when you show the 2 pz orbitals from the carbon, you show them higher than oxygen and nitrogen and halogens. Okay, so so if you had, for example, nitrogen here, oxygen, or let's say fluorine, those 2 pz orbitals will be lower in energy compared to the 2 pz from the carbon. So this is basically something that has been calculated, yeah, and it's just basically this is how we need to deal with that. As also the hydrogen will be lower in energy compared to carbon.
So all
okay.
the halogens and hydrogen will be lower in energy, right, than carbon?
That's correct. Yes, they will be lower in energy. Yes. At least, for the fluorine, of course, if you think about, then you have, for example, bromine. Okay, so you will not be using the 2p z orbitals from the bromine to form this what is it called, to form the sigma bonds or pi bonds. Yeah. So therefore, therefore you need to look at this little tree here, and then you will see in this tree that there will be probably a little bit higher in energy. But if you're talking about the elements in the same row, well, the oxygen, nitrogen, and fluorine, they will be lower in energy. Okay? And hydrogen too, yes. Okay, so let's move on to a little bit, more complicated systems. Okay, so here we have a molecular orbital diagram for acetate ion. So acetate ion basically is the ion that is formed between two oxygens from the acetic acid that has been deprotonated. Okay, I mean that from acetic acid that has been deprotonated. So you have CH3, C, double bond O, O minus here. If you draw the proper Lewis structure of this molecule, you will find out that there are 2 lone pair of electrons here, and 3 lone pair of electrons on the oxygen at the bottom. And we're gonna talk about it tomorrow. But those electrons from the oxygen at the bottom can be delocalized between these 2 oxygen atoms. Okay, so what you can do, you can use these electrons from the bottom here, one of the pair of electrons, move it towards the carbon, and at the same time the double bond will move up to the oxygen. By doing so, you draw something what is called a resonance structure. For the resonance structure, you draw the double arrow here, okay? So what you're gonna end up here now is CH3C. Now you have a single bond because you just broke the double bond up, and you have an oxygen with now 3 lone pair of electrons and the negative charge on top, and the double bond and oxygen with 2 lone pair of electrons at the bottom. So the probability of having this negative charge on the top oxygen here, top oxygen and the bottom oxygen, is the same. Okay. So how do you describe the molecular diagram of this particular system? Well, what you normally show here is only the orbitals, in this case the p orbitals, that are involved in the delocalization of this negative charge. So you can use only p orbitals here, okay? Because in order for you to delocalize the electrons, you have to have the orbitals oriented properly, and they have to be in line on the same plane. And by doing so, it means that they cannot be sp3 hybridized or sp2 hybridized. They have to be just basically p orbitals. So the localization occurs only on the p orbitals here. Okay, and so that means that if you look at this particular acetate ion here, you have to have the p orbital on both oxygen, carbon, and another oxygen. And this is what you see here drawn at the bottom. Okay, so at the bottom you see that there are 3 atoms connected with the central atom in the middle, which is the carbon. Okay, I'm going to draw it back again here. So we have a carbon here, and you have 1 oxygen here and 1 oxygen here. We know also that there is a negative charge located either on one of those oxygens. Okay. So either top or the bottom. So that means that there must be at least 2 electrons that are present on either one of those two oxygens. So either on this guy here or this guy here. These are 2 extra electrons that will give you this negative charge. Okay. So what do you see here on the right side here is 3 different possibilities that you can have for the electron distribution. As you can see, from the resonance structure, the negative charge can be localized only on the oxygens. And what do you think, if you look at any of those 3 structures here, which structure represents the situation when the charge is localized on the oxygens? The bottom one, middle one, or the top one? What do you think? Okay, the middle one, correct. So the middle one shows you two electrons that are localized on either this oxygen or that oxygen, because there is a node here. Okay, in this particular situation on this carbon there is a node, so that means that there is no p orbital that is oriented. So the possibility for the resonance is shown at the bottom structure. So the bottom structure here shows you that there are three p orbitals on each and every one of those atoms, and they're aligned, so therefore electrons can flow from one side to another. Okay, but to lock them only at two positions, you have to have them the middle structure here. Okay, because that means that the electrons cannot flow through this carbon here. Okay, and because of that, they have to be either localized on the oxygen on the right side or on the left side. Okay. And then the last structure here is the anti-bonding orbital. So basically, there's you know the signs of the functions here. You see, they are all opposite. So therefore the electrons cannot flow directly. Yes. What was the question?
Yeah, Professor, I have a question on the diagram that you drew for acetate, the bottom left. If you count electrons on oxygen, they add up to 9. If you count with the negative.
So here what you have to look at is that you have to look at the pi electrons that are present in the molecule. So 2 pi electrons from the double bond, and 2 pi electrons from the negative charge from the lone pair of electrons. So that's 4 electrons together. Okay, that's why you only show those 4. The rest of the electrons are involved in the sigma bond formations, and you don't care about those. You only care about pi electrons, because only pi electrons can be moved in resonance structures. Sigma electrons cannot be moved.
So for resonance structure, atom can have more than 8 electrons on it?
Oh no, all of those atoms, they have just 8 electrons. They don't have more.
If you for the oxygen,
where do you see more electrons?
Oxygen on top, you have 1, 2, 3, 4, 5, 6, 7, 8, and then you have negative sign. Doesn't that represent another electron?
Oh no, yeah. So the negative sign is me just showing you, telling you that there's a negative sign, but the 6 electrons plus the sigma bond, that's together 8.
No, I'm talking about the bottom diagram. The bottom diagram.
Yes, in the bottom diagram, you have the sigma bond here, okay, and 1, 2, 3, 4, 5, 6. Okay, so because you have these 6 electrons, therefore there is a negative charge on this oxygen. So you have to show somehow that there is a negative charge. So this negative charge basically tells you a formal charge of the oxygen. It's not electrons, additional electrons that you are adding to the structure, to the Lewis structure. This is just the way to show that there is the overall charge of this oxygen is -1, or the formal charge of this oxygen is -1.
Got it. And
okay.
I don't understand how you switched the bonds. The bottom one had double bond now. Like on the top diagram, the bottom one had single bond.
So this is called the resonance. We are going to talk more details about the resonance tomorrow. Okay. So don't bother too much about it. Just need to understand that there is a resonance, and if you have a possibility for the resonance structures, the molecular diagram will focus only on pi electrons. Okay. Not sigma, unless I'm asking you specifically about the sigma bond between 2 different atoms or something. You will have to consider for the molecular orbital diagram. You'll have to consider on the conjugated systems. You'll have to consider only pi bonds.
Professor, I have a question.
Mm-hmm.
So back to the cartoon. So in the middle, you said that that's the image that shows that the electrons are localized on the oxygens, right?
That's correct. Yes.
And that's because there's no p orbital for carbon, so that means that the oxygens can't travel to the carbon.
Yes, basically, it's not. That means that electrons cannot travel through from one oxygen to another. Only the bottom structure allows you to do that, because you see all the wave functions on the p orbitals are oriented properly here, so they are in line on the same plane of symmetry.
So the p orbitals are the ones that let electrons travel from atom to atom?
Yes, that's correct. Only p orbitals, not sp, sp2, and sp3 orbitals. Only p orbitals allow you to travel, electrons to travel.
Okay. Okay.
Okay, so yes.
With the oxygens on the left diagram for resonance, then the ones with the negative charge, is that due to a formal charge?
So this is the formal charge of this oxygen. That's why you put the negative over there. Yeah. If I left only 6 dots, you wouldn't know that there is a negative charge here. Yeah. Correct? Unless you just, unless you just show it. So this is how you show it. You basically put a negative charge over there. The same is with positive charge, though. So if you have a molecule that has a positive charge, well, then this is what's going to happen. Okay. Nick. Okay. So just 1 second, Deborah. Okay. What is showing in terms of electron localization? Okay. So we have 4 electrons. These are 4 pi electrons in here that are present in our acetate ion. So we have 1 lone pair of electrons that is on the p orbital, and we also have a double bond that shows 2 electrons. Okay, so those that uses 2 electrons. So those are our total of 4 pi electrons. The rest of the electrons are sp2 hybridized in this molecule, so therefore you don't count them. Okay, so energy-wise, you see that the electrons are localized mostly on the oxygens. Yeah, so the highest electron density is shown on the oxygen either on top or at the bottom here, and the middle structure here shows you the localization of those. Okay, so that means that the electrons can be localized only on those oxygens, not in the middle of the carbon here. Okay, and the ability for the double bond to travel between 2 oxygens is shown at the bottom structure here. So that this is your pi bond, the double bond that moves between between these 2 oxygens. Okay, and it is possible because right now all the p orbitals are aligned properly, and the wave signs of the wave functions that represents each and every p orbital is properly aligned too. Okay, so this bottom part is your double bond. The middle part here is the actual the p p orbit it's the electrons on the p orbitals on the oxygens from the lone pair. Okay. And the top part is the anti-bonding situation, so no electrons, nothing there. Okay. Okay. So what's the question?
For the middle structure, so would that be the situation in which both oxygens have a negative formal charge because there's no p orbital to form a pi bond?
Well, the idea is that, of course, this is just a theoretical situations where you have the negative charge localized on either one of the oxygens. In the real life, it's a hybrid structure. So I agree that there's there will be a partial negative charge on each and every one of those oxygens. But but also because of that, the oxygens, both oxygens, even though, for example, you have a single bond here, yeah, on this in this particular case, you would think that, for example, this oxygen is sp3 hybridized, but it's actually sp2 hybridized because of this ability to delocalize this the negative charge. So in the structure at the bottom, the oxygen has a negative charge and single bond, and the top it has a double bond. Okay, so because of that, you can clearly see that they will have a different hybridization. But in general, of course, like you said, the overall structure would be better represented by. I'm sorry, not like this. is my eraser here? By the structure that looks more like this. Okay. So this way, the negative charge is delocalized between both of the oxygens. Okay. Next question. Oh well, this is just an orientation of the orbital. So basically, it's just a node here. Okay. So it's no longer there. So it's either different direction or So any of the situations where you can imagine the p orbital is not aligned with from the carbon is not aligned with the p orbitals from the oxygens is valid over there. Okay. Yes, Chantal.
Sorry, I didn't mean to put my hand up.
Okay. Okay. So let's go to the next example. Okay. Here we have two molecules. Okay. So one molecule is it's a propene molecule, so it has the 3 carbons and the double bond here. Okay. The other molecule is called a allylic carbocation. Carbocation because it's a carbon with a positive charge on it. And as you can see here, this carbocation now can, or the positive charge on this carbocation can be delocalized between 2 different positions here. So if you take the pi bond here, and I told you only pi bonds can be moved in the molecule, if you move them towards the carbocations, you deplete carbon number 3 in electrons, and therefore the positive charge will move from carbon 1 to carbon 3 to form its resonance structure. Okay. Well, and that will be our molecule B. Let's call it this way. Okay. In molecule A, you cannot do that because in order to move this double bond to be between carbon 1 and 2, you will have to actually move the hydrogens from the CH3 at carbon 1 and move them towards the carbon number 3. And we cannot do that with resonance. But because of that phenomenon, you will draw a different energy diagram for both of these molecules. Okay. So if I were to ask you about the energy diagram for the pi bond of molecule A, okay, so the A is on the left side, okay, then you know that you have energy here. You have 2 carbons, so therefore you start with the 2 orbitals that have the same energy. This will be our, let's say, carbon number 2, and this is carbon number 3. Okay, and we are talking about the pi bond now, not the sigma bond. Okay, so the pi bond here is formed between 2 pz orbitals from both carbons, and we have 1 electron on each 2 pz orbitals, and there we go. You form a pi bond with 2 electrons, and of course there is an pi anti-bonding orbital with no electrons. Well, the localization on electrons in molecular orbital theory happens only if you have a conjugated pi system. In the otherwise, you don't show the localization of electrons. You just show each and every molecular orbital separately. Okay, so for each and every bond that you form a different. You can draw the different molecular orbital diagram, or you can combine them all together into one big molecular orbital diagram. Okay, so going back to this the molecule A. So because of that, this is our situation, okay? And we know that the 2 pz orbitals, they look like 8s, and they have this let's say 2 different signs of the wave function, and both of them has to be oriented the same way, and also the sign has to be on the same side of the double bond. And then the bonding scenario is when these two 2pz orbitals interact with each other, and they form this molecular orbital, which is the pi bonding orbital. And then anti-bonding orbital it's much easier to draw actually, because all you have to do is just draw 2p orbitals with the wave functions on the opposite sides. Okay? Yes?
Yeah, so so if we wanted to show the whole diagram, whole molecular orbital diagram, we would show two we would show two sp2 orbitals combining with each other, right? Below the 2pz orbitals.
Well, if you want to show the whole molecular diagram for this molecule, you have to show for, let's say, carbon number 3, okay? Because it will depend on which atom do you.
Carbon 2 and 3.
Let's say that's carbon number 3. If you want to show the full molecular orbital diagram for carbon number 3, you would also have to show 3 different sigma bonds there. Because there is a sigma bond between carbon 2 and 3, and there are also 2 sigma bonds between carbon 3 and 2 hydrogens that are not shown on the structure, because this is the line angle formula. Okay? So total number of the bonds will be 4, because carbon forms 4 bonds. It doesn't matter if it's double, triple, or single bond.
Yeah, show those 3 sigma bonds. I'm saying, can we take 2 sp2 orbitals and combine them? Would that represent those 3 orbitals, 3 sigma bonds?
I'm not sure if I'm getting what you're asking for. How do you want to combine them?
Yeah, can you just draw it if you have time? If you could draw the 3 sigma bonds, how would you draw them in this diagram?
Okay, so you draw them just below the, of course, below your 2pz, yeah, and they will yeah. Let me finish this, and then I can draw the example of that. Okay. Yeah.
Why is it 2pz? Like, how do you know if it's 2py, 2pz, 2px?
Well, this is because it goes above the it's perpendicular to the sigma bond. Okay, so normally what you do is that when you look at the axis, you have px, py, and pz direction. So anything that is perpendicular to the main structure is assigned automatic EZ. It actually doesn't matter. Okay, the most important part here is that if you choose to, for example, py, you have py to py, for example, orbital, you have to use the py all the way. Okay. Do you know what I mean?
Thank you.
Mm-hmm. But it's safer to just to do the pz. Yes.
Would both carbons have to have like the same orientation for the p orbital that's available for them to transfer the resonance structures? Because the middle carbon would have only one p orbital.
That's correct. They will have to have the in order to delocalize the charge, they will have to have all 3 p orbitals from each and every carbon oriented the same way with the same wave function sign.
Okay, thank you.
The spheres at the bottom here, these are kind of elongated spheres, Daniela, okay? So these are the electron densities. So this is the graphical representation of the pi bond, the pi bonding interaction, not anti-bonding. Anti-bonding is on top. At the bottom is the pi bonding interactions. This is what you need to remember. You need to be able to recognize it as a pi bonding interaction. Okay, so if you look at the B molecule now, this is something slightly different. Okay, because right now we have a delocalized system, and because it's the localized system, you are not going to show the energy diagram that looks the same as the one from the A molecule, because there is no delocalization here, but you will show something that is very similar to the acetate ion, and this is actually a great thing for you. The only exception you will have here is as follows. So on the right side here, you're going to draw the how many electrons are on each and every orbital. So what do you think? How many electrons will be here? In the acetate, which has the negative charge, we had 4 electrons. So if you have a positive charge, how many electrons will you have? A total number of electrons. What do you think?
Or 2.
Just 2, yeah, because you have only pi bond, yeah, an empty p orbital. So there will be only 2 electrons, and they will be localized here, yeah. Now, you know, as far as the shapes of the orbitals, well, there you go. You just draw exactly the same MO diagram that you would have drawn for the acetate. Okay, and the bottom one shows you the localization of the double bond. So that means this is the diagram that allows you to move the pi bond between carbon, carbon, and carbon. So carbon 1, 2, and 3. Okay. The structure in the middle shows you the structure that explains again the electron density, or in this particular case, the lack of electron density between carbon 1 and 3. Okay, because basically that means that there is a positive charge here on this carbon or positive charge here on that carbon. And the last part is then anti-bonding orbital, which is basically you don't care about that, yeah, because you don't want to have electrons on that. The diagram on the right is called molecular diagram for conjugated systems. Okay, so this is molecular orbital diagram for the conjugated system. So the one on the A part is non-conjugated. The B part is the conjugated system for the B molecule here. So you see in this case here, in the acetate anion, we had 2 additional electrons that will give us our negative charge. Yeah, and at the in our particular case, the symbol that I drew shows you an empty orbital, basically, you know, the lack of electrons, basically. Okay. Yes, Jacob.
Oh, sorry, I just had my hand up from last time.
Yes. So, so the idea here is as follows. Okay, Gunit?
Yeah, can we draw the non-conjugated for B2, or is it impossible to do it for the?
No, because you cannot delocalize. There are no p orbitals on the carbon number 1 here. Look, carbon 1 is sp3 hybridized. This is sp3 hybridized, sp2 and sp2. In order to delocalize the charge, your carbon has to be sp hybridized, sp2 or sp hybridized. You have to have a p orbital empty or with electrons available for the electron delocalization. Otherwise, you won't be able to draw this diagram, because basically the whole left part here, I'm not going to draw it, but the whole part here, this part here, will not be able to participate in the localization, and therefore you will have just this scenario that is already drawn on the left side. Okay? So this scenario here is possible only and only with the molecules that do have at least 3 atoms connected together, and there is a possibility to localize either positive, negative, or a radical charge. Radical will be the situation when you have just a dot here instead of plus. So dot means radical usually in the structure. Okay, and so here we had the MO diagram of the pi bond of this molecule A. So what if we had this? We wanted to show the sigma bond here between carbon 2 and 3. Okay, so this is actually quite nice here, because we are talking about 2 sp2 hybridized carbons now, orbitals now. Okay, each and every one has 1 electron, and they form a sigma bond and sigma anti-bonding orbital. And there are 2 electrons on the sigma bond. So you see the diagram looks actually exactly the same as the pi bond here, with one exception. These are sp2 hybridized orbitals now that are involved in the formation of the sigma bond. And also, they have a different shape. So we have, oh my God. We have the one sp2 orbital, and then we have another sp2 orbital. And when they combine together, they form the sigma bonding orbital that I usually draw like this. And then, of course, anti-bonding scenario will be very similar to what we drew before, but just change the signs of the orbitals. And there you go. So the main difference in drawing the sigma bonds and pi bonds will be the cartoon version of those orbitals. Okay, so bonding molecular orbitals and anti-bonding orbitals, and also the identification of the atomic orbital that will form. Of course, you know, this is sigma, so you have to label it sigma. Yes, Gunit?
Yeah, so this is between carbon 2 and 3, the sigma bonds?
This is between carbon 2 and 3. So this is carbon 2 and this is carbon 3.
Yes, this is what I was saying earlier to show the.
Okay, so let's say right now you want to combine sigma and pi bonds. Okay, so we are talking about the whole double bond, so sigma and pi bonds between carbon 2 and 3. Okay, so we have carbon 2 and carbon 3 here. So the first thing you do, you want to draw yourself an sp2 hybridized orbital, and then above that there is a 2pz orbital. Okay, on the other side there will be 2 the same orbitals. Each and every one of them will have 1 electron. Okay, we know that the sigma bond is the one that has that is the strongest, so therefore it will lower the energy the most here. And the anti-bonding interaction will be even stronger, yeah? Sorry, just not a perfect draw. So we have a sigma bond here and sigma anti-bonding orbital here. And we know that 2 electrons from sp2 orbitals will go down to the sigma bonding molecular orbital. And then you have the pi bond here that will form, it will form between 2 pz orbitals, and that will form like this. So we have a pi bonding and pi anti-bonding orbital. And again, both electrons will go to pi bonding orbital. Yeah.
Professor, why would there not be 2 orbitals for the pi?
Because we have only 1 double bond here. How many double bonds do you have here? Just 1, yeah? The double bond is sigma bond plus a pi bond. A triple bond is a sigma bond plus 2 pi bonds. So this is not a triple bond, this is a double bond. That's why you have only 1 pi orbital. We are not showing here, in this diagram, I'm not showing the sigma bond formations between carbon and hydrogen. This is just carbon 2 and carbon 3. Okay, yes, Gunit?
Yeah, so let's say if you only had a single bond, right? Then we would show 2 sp3 orbitals combining with each other, and we would have no p orbitals, right?
Well, there will be no p orbitals if you show only the sigma bonds for the sp3 hybridized molecule, because all p orbitals are involved in the hybridization. So there are no free p orbitals available for the pi bond formation. Okay.
Yeah. So just sp3 just combine them, right?
Yes, so this is, so yes, so basically what happens here, yes, so what happens here in this diagram, we are just showing a double bond, so this bond here and the pi bond here. So let's say that this is the sigma bond and this is the pi bond that we drew the molecular diagram of. Okay, if you want to add the, you know, the, for the carbon free, for example, you will want to add the, oh my God, the those H's here. And for carbon 2 another H, you will have to extend it. You know, you will have to extend those diagrams just to show this CH bonding. Okay, but nobody does that. Okay, so people usually try not to do that. You know, usually you show the important part that you are interested in. And if you have other parts of the molecule that you want to show, you just show them separately. The only thing you want to do, you want to keep in mind that you have to show them in the, with the proper level of energy level basically for each and every orbital. Okay, but again, for us, the most important part that you need to remember is that you need to be able to draw the molecular orbital for the single bond, double bond, a triple bond, okay, or recognize it. You need to be able to recognize the shapes of those orbitals, the atomic orbitals and molecular orbitals. Well, so this is something that I want you to do, okay? So, Deborah, okay? So the shapes of those orbitals, you can look at the previous slides and you can draw them right next to one another. And then if you still feel like that there is something wrong going on there, just post it on the discussion board and we can definitely, you know, have a look into it, okay? Now let's talk a little bit about the MO diagram for the diatomic molecules. Okay, so diatomic molecules like fluorine, oxygen, halogens, they, you know, those molecules or nitrogen, they exist in nature not as a atomic elements, but they exist as a diatomic elements. And because of that, you know, you can easily draw the MO diagram for those. But the first thing you want to start with is the, you know, it's the Lewis structure of those. Okay, so drawing the proper Lewis structure of the molecule allows you to draw the proper MO diagram to, you know, to a certain extent. So first of all, Lewis structure will tell you, do I have a single bond, double bond, triple bond, whatever, yeah? And then the, and also it will tell you how many valence electrons do you have, yeah? So if you don't remember that, you know, you can always look at the group number. For the main groups, it's gonna be the number of the valence electrons will be the group number. So the fluorine has how many electrons? How many valence electrons? 7, yeah, 7 electrons. Okay, so if you were to write down the electron configuration, you have 1s2, 2s2, 2p, 5. Okay, so 7 valence electrons. Okay, I'm gonna put the V here. Okay, and our 7 electrons are on the valence orbitals. So the so the 1s orbital is not involved in any kind of bond formations or anything like that. Okay, so the so you don't draw it on the MO diagram, but what you can draw here is the remaining orbitals. Okay, and the so that means that we have an 2s orbitals and 3 p 2p orbitals. Yeah, so 2s and 2p. Okay. And we know that 2s orbitals, they have 2 electrons, and then p orbitals will have 5 electrons. And of course, this is one of the fluorines. On the other side of this structure, we have another fluorine, okay? 2s, 2p, okay? And there are 2 electrons here. 1, 2, 3, 4, 5. Okay, so the orbitals with the same energy will react with one another here. So therefore, the 2s will interact with 2s, and you're gonna form a sigma bonding and sigma anti-bonding orbital. We have 4 electrons fill up the 2 molecular orbitals, so therefore we'll fill up both of those. And then we have the p orbit, and then we have the p, x, y, and z orbitals. So x, y, and z. Yes, Gunit?
Yeah, Professor. So in the previous diagrams that we drew, we had sigma star like all the way at the top, as the highest energy level. Why are we drawing it?
I'm sorry. Could you repeat, please?
So on the previous diagrams, we had sigma star all the way at the top, right? And in
Yes.
this diagram, we have it right above sigma.
Yes.
Right.
So this is so. Look at the designation for this orbital. It's 2s orbital, not sp orbitals, or sp2 or sp3 orbitals. So it's basically a different level of energy for an atomic orbital here, not hybridized orbital. So in this case, you just basically show them as separately, and then since the let me tell you this. Okay, let me finish the drawing the whole structure here, and then it will become clear to you like why is it this way or the other way. Okay, not the other way. So in here, what happens here is that we have 2p orbitals now, x, y, and z. So the orbitals from x-oriented, they can interact with one another to form a sigma bonds. And we will have another. So this will be sigma 2s, and this is going to be sigma 2p orbital. And this will then have also an anti-bonding orbital, so sigma 2p anti-bonding. Okay, and then that means that once you lock one of the bonding scenarios, okay, that means that the other p orbitals they have already fixed orientation that is perpendicular to this first sigma bond. So that means it has to be pi orbital, and you will have 2 of them. So you have a pi y and pi z orbital, and also, of course, a pi anti-bonding y and pi anti-bonding z orbital. So now at this point, all you have to do is just fill up the remaining electrons. I'm going to do it in blue. Okay, so we have total of 10 electrons here. So we're gonna have 2, 4, 6, 7, 8, 9, 10 electrons now. Okay, so do you remember when I told you at the beginning? When you have the electrons present on the orbit, on the bonding and non-bonding, the same number of electrons on the bonding and non-bonding orbital, let's say sigma or pi, they cancel each other. Okay, and because of that, the 2s electrons here, we have an anti-bonding and bonding electrons. Basically, that gives you a bond order of 0. So the only thing that can affect the actual bond order here, so tells you that this indeed is a single bond, is the interaction, are the values that you can get from the calculations in the on the 2p orbitals. And think about it this way: for the 2p orbitals, the bond order will start with the electrons that are on the bonding orbitals, and we have 6 electrons here, 2 on the sigma bonds and 4 on the pi bond, minus now the number of the electrons on anti-bonding orbitals, and in this case we have the electrons on the y and z orbitals, and there are 4 of them, and you divide it by 2, so that's 2 over 2 equal 1. So in this scenario, like you may think, oh, I have electrons on the pi bond, on the pi bonds here, but because there are also electrons present and an equal number of electrons present on the pi anti-bonding orbitals, basically they are not involved in the formation of the of the double or triple bond, and therefore the bond order here will be just 1. Okay. So, yes.
So, Professor, so for the 2p, right? Pi y, pi z, around that area, you drew 3 orbitals, right? 3 orbitals. So that's 6 electrons, and then for the circles that you drew at the bottom, that's 7, 8, 9, 10. So doesn't the bonding orbital electrons, don't they add up to 10?
No, because let me change the color here. I'm going to do in green only bonding electrons here, okay? This guy here, and this guy here. Okay, these are 6 electrons that are on the bonding orbitals. These are on the sigma and pi bonding orbitals.
So we don't count the 2s ones?
2s ones, yeah, if you want to do that, well, you can do that, of course, yeah, but then then you would add only those as a bonding, because the other ones are anti-bonding. So if you follow only the, let's say, a green pathway, and let's say I'm gonna mark as a purple the anti-bonding.
Yeah, it will still be the same. Yeah, 8 minus 6. That's
so that will be 8 minus 6. Yeah. By 2.
Okay.
Yeah, so that's why I said, if you have just one orbital, for example, like in this case, s orbital that have electrons on both bonding and anti-bonding, just basically you don't even bother to count them, because that's going to be 0 for your bond order. So you want to look farther up. So you can imagine that the same diagram will be drawn for O2, N2, Cl2. The only difference is that for the Cl or Br2, you will have different orbitals, so not 2s but 3s or 4s, and then 3p orbitals, for example. Okay, but if you think about, for example, next molecule, let's say an oxygen, yeah. For the oxygen, how many valence electrons do we have on oxygen?
6.
Oxygen has 6 electrons, 4 valence electrons, or 6? No, 6. 6 valence electrons, yes. 6 valence electrons. Okay, so if you have 6 valence electrons, they are on 2s2, 2p4, 2p4 orbitals. So again, if you draw the MO diagram for them, this is what you will end up with. You have a 2s and 2p, and of course 2s, 2p, 2p orbitals, x, y, and z, x, y, and z. You have 2 electrons on 2s and 4 electrons on the 2p orbitals. So you're gonna end up getting the this is gonna be a little bit flatter drawing. Sigma bond and sigma anti-bonding orbitals formed for the 2s, and 4 electrons over there. So basically no gain here. And then you will have sigma and 2 pi bonds form for 2p orbital. So we have a sigma 2p, and then you have a pi 2p x and y, and then you have a pi anti-bonding 2p. I'm sorry, I'm sorry, this is z and y, and this is going to be 2px, and sigma anti-bonding 2px. Okay, and all you have to do is just fill up the electrons here. I'm going to do it in red now. So we have 8 electrons total. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, what is the bond order of the oxygen bond?
Oh, 6.
So 6 minus how many?
2.
Minus 2 divided by 2. That's 4 by 2. That's 2. That means you have to have a double bond here between the oxygens and 2 lone pair of electrons. There you go. Yeah. So for these biatomic molecules, the energy diagram always looks the same, or almost always looks the same, okay, let's say. But for the molecules that I will ask you would be maybe oxygen, fluorine, or nitrogen, carbon. This is because you have to choose, again, you need to choose arbitrarily the axis along which the sigma bonds will form, and usually x is the axis that you choose. So we have px, py, and pz. If you look at the orientation, what is this? Where is the? Okay, I'm sorry. 1 second, okay. There we go. If you look at the okay, control. Okay, if you look at the what the hell happened here? Just 1 second, okay. Okay, there we go. If you look at the 2p orbitals, those 2p orbitals, they are oriented in the 3 dimensions along 3 different axes. Okay, so we have x, y, and z axis. So px, py, and pz. Sorry for quality here. Okay. So if you form a sigma bond, that means the px orbital has to interact with another px orbital. So assuming I'm going to do it in the different color here, let's say green one. Assuming that this is our carbon, this guy here is our carbon number 1, and you want to make a carbon-carbon bond with carbon number 2, you will have another diagram, x, y, and z, and the sigma bond will form only between px's here. Okay, so only px can interact here with another px to form a sigma bond, assuming that the sign of the wave function will be the same for both. Okay, and then you will form a sigma bond here. Okay, but at the same time, you see that the pi bonds are now locked and they are perpendicular to the sigma bond, so they can form only pi bonds. Okay. Oh, anyway, yeah. So I think we ran out of time, so this is going to be our last slide. Do you have any questions before we go? Yes, Gurneet?
Oh no, it was already on from earlier. But I just wanted to say something. If you could please upload the slides from.
Yes. So the slides, those slides are available, I think, already. the resonance slides will be available today. Yes, so I will upload them. As far as the notes goes, I think I said last time that I'm not going to post the slides with the notes. You have to take your own notes on the slides that that I posted for you. So this way you can keep pay attention.
Okay, thank you.
Okay, and you're talking about 6 here in the bond order, Devin. You count only 2p orbitals because 2s already have 4, so this is 2 minus 2, that's 0, yeah? So only 2p orbitals actually make a difference here. So you have 6 electrons on the bonding orbitals and 2 electrons on anti-bonding orbitals. So 6 comes from the just bonding orbitals. The only thing, when you look at those, all you have to do is just look at those and see, oh, there is no star here by pi or sigma, so that means you have to add those electrons together and subtract anything any electrons that are on the orbitals with the stars.